Alrighty, quick video of the limit comparison test. So if the limit of a sub n to b sub n is a positive finite number, then both series will do the same thing. That's why it's so important to take that limit if it's an FRQ. If it's not, then you don't have to worry about it. You can use a P series, geometric series, whatever you come up with. But it's really, really important that the limit of this ratio is equal to a positive finite number. Now, most of the time when we do this, our limit is always 1. That could change. It doesn't have to be 1. It could be 2 or 3 or whatever. As long as it's a positive finite number, then what it guarantees is that a sub n will do whatever b sub n does. Okay? So, the limit is super important in the limit comparison test. Thus, limit comparison test. Alright, so here's a simple example, right? We have this series, and we're going to use the limit comparison test. So we're going to create our new series, which will be the biggest thing on the top divided by the biggest thing on the bottom, and that reduces to 1 over n squared. Now, I know this is a convergent P series, right? And technically speaking, if this is multiple choice, since this converges, I know the original series will converge. However, if I'm faced with a free response type of a question, I must show that the limit of the ratio of the original to the new, the one we created, is equal to a positive finite number. In this case here, I have n squared times n squared is going to give me n to the fourth on top over n to the fourth on the bottom. So the limit is just the ratio of leading coefficients, so we get a 1, okay? So what this guarantees is that my original series is going to do whatever the created series is going to do. Since our created series converges, right, p is greater than 1, so it's going to converge. So that means that our original series is going to converge not by a P series test, but by a limit comparison test. In another case here, I've got 1 over 3 to the n minus n, so biggest thing on the top over biggest thing on the bottom. And what I see is that this is a convergent geometric series, right? R is equal to 1/3. And if I take the absolute value of 1/3, I get 1/3, which is less than 1, so I know that that's going to converge. However, if I'm faced with free response, I'm going to have to show the limit of the ratio of this thing, right? So, sometimes you got to go through a little bit of work, like reapplying L'Hopital's rule a million times, but anyway, if I plug infinity in here, I get infinity over infinity. So I used L'Hopital's rule. I think I did this same problem in class at one point, or something similar to it. Anyway, I used L'Hopital's rule and took the derivative of the top, derivative of the bottom, plugged infinity in again. I still have indeterminate form. So I used L'Hopital's rule again, and at this point here, everything top and the bottom cancels, and we get the limit of 1, which is 1, okay? 1 is a positive finite number, and so therefore the original series 1 over 3 to the n minus n will converge by the limit comparison test. Hopefully the dog's not going to go nuts now. Here's another one, okay? Again, really simple. If I take what's on the top and what's on the bottom and I write it as a ratio, it's clear that that's a divergent P series. Why? Because P is equal to 1, and the rule says that when P is less than or equal to 1, then the series will diverge, sorry. So I know this is going to diverge, the created one, okay? But again, I need to show this divided by this, which is just the same as the original times the reciprocal. And, I get n over n plus 1, the degree of the numerator, same as degree of denominator. So when I take the limit, it's just the ratio of leading coefficients. I happen to get a 1, and so this guarantees that whatever this does, that does. Since this diverges, the original series is going to diverge. Here's another one involving an ln n. So biggest thing on the top's a1, biggest thing on the bottom is n squared. That's a convergent P series. Showing the limit of the ratio of the original to the created one, or the new series, b sub n. What we get is n squared over n squared minus ln n. Now remember, I can't do this. I can't cross those out because this is not a single term on the bottom. So I'm going to have to use L'Hopital's rule. So I did that. Plug infinity in again, have an indeterminate form, L'Hopital it one more time, and then I'm going to have 2 over 2 plus 0 if I plug infinity in, which is going to be 2 over 2 or 1. So I end up with a positive finite number. So that means that the original series is going to do whatever the new series we made is going to do. This converge, so this will converge. And finally, one more. Again, this is pretty simple. Biggest thing on the top is, you don't have to put the 5, by the way, but you can if you want to. It doesn't matter. I would leave the 5 out because it might confuse you, but remember, it's the variable to the highest degree on top and over the bottom. So you can just write it like this, Divergent P Series. If this is multiple choice, I'm done. I have my answer, right? But if it's free response, I need to show the limit of that ratio, and the limit happens to be a 5, which is good because I wanted to show you that. For most of the time, ours is always ends up to be 1, but this is still a positive finite number. So that means that the original series will do whatever this one does, okay? And I put converges here, and this should be diverges. See, that's what happens when you have too many convergent examples. You automatically write the wrong thing. Okay, so anyway, that's the limit comparison test in a nutshell.